Good afternoon, everyone. My name is John Cardenas. My topic for this homework assignment is waste reduction of polypropylene bag manufacturing process using the Six Sigma DMAIC approach. This article was written by Muhammad Usman Jan from the Department of Industrial Engineering, University of Pakistan. Among the three different methodologies followed by Six Sigma according to different scenarios and situations, DMAIC is the best strategy. It is utilized for minimizing production time by cutting off unproductive steps, define, measure, analyze the problem, and then control and improve it, and focuses on continuous improvement of processes. This is my actual agenda for my homework assignment with a conclusion at the end. The first step under DMAIC is define. Under define, we will cover problem statement, scope of improvement, intended objective, and identifying the customer, the stakeholders. Problem statement. The improper disposal of used polypropylene has a colossal adverse effect on the environment and on the ecosystem. This is also a major contributor of environmental degradation. In addition, this high rejection rate has a direct and adverse effect on the profit margin. Keywords on the problem statement are environment and profit. Objective. The researchers aim to reduce the environmental impact of the plastic waste. The current research project aims at devising the efficient manufacturing process to have a minimum plastic waste in the first place. Scope of improvement. Current annual rejection rate is at 2.8. The scope is to reduce the rejection rate by 45% to 55%. Improving current processes will enhance the company's profitability and image. Stakeholders, the customer. End user identified as an internal customer. The next step under DMAIC is measure. Under measure, we will cover identification of the area to be focused, identification of key process input variables, and key process output variables of important areas. Identification of the area to be focused. It has been planned to see the dispersion of rejection data by each department for the significant variables to be identified. Those areas include extrusion, weaving, cutting and stitching, printing, packaging. The weaving department has reported 81% of SAC's rejection. Data in Pareto chart clearly identifies the weaving department as the highest in rejection. Identification of key process input variables and key process output variables. Tape quality is selected because it is the final output of the extrusion line, and all KPOVs are measured for tape quality, which finally becomes then a key PIV for the weaving department. The mean SAC rejection for the weaving department is 2.27%, causing about 81% of the SAC rejection. In conclusion, the weaving department is causing the highest rejection rate among all departments. The next step for the DMAIC is analyze. Under analyze, we will cover identification of significant key process output variables for Y of weaving department, identify critical key process input variables for X. Identification of significant key process output variables, Y is of weaving department. Size, elongation, and strength of the fabric are some of the critical output variables. The hypothesis testing and confidence intervals have been planned to be used to identify the output variables that need to be improved. Critical output variables will be tested to help identify which one need improvement. To perform hypothesis testing for key process output variables, 5 weaving loom machines are selected and each key process output variable is measured 5 times. To check whether the mean of each key process output variable is equal to the required process standard or not, the same one t-test has been used. The hypothesis testing for the 3 parameters fabric size, fabric elongation, and fabric strength is conducted and the results of the test are recorded. Table 6 shows that HO, the fabric mean size, is equal to 50 centimeters, the required process standard. Table 7 shows that fabric mean elongation is greater than 18%, the required process standard. Table 8 shows the result of null hypothesis, which states that fabric mean elongation is equal to 70 kgs, 5 centimeters, the required process standard will fail to be rejected. Hence, fabric strength has been identified as the most significant key process output variable during the above hypothesis testing. Identify critical key process input variables for X. Cause and effect matrix. Tape quality is the most significant. Hypothesis testing is used to identify the output variable that needs to be improved. To perform hypothesis testing for each key process input variable, 25 bobbins are selected from the extrusion line and one sample t-test is performed on each key process input variable. Identify critical key process input variables for X. Hypothesis testing for the mean tape width. Table 10 shows that the mean tape width is equal to the required process standard of 2.6 millimeters. Tape 11 shows that the mean tape denier is equal to 950 grams, the required process standard. Table 12 shows that the results of null hypothesis, which states that tape tenacity is equal to 6G denier. The required process standard is rejected, as p-value is less than 0.05. Results. Hence, tape tenacity is identified as the most significant key process output variable during the above hypothesis testing. The current focus is to identify the critical input variables that drive variation in tape tenacity. The input variables influencing directly the tape tenacity are decided to be analyzed. In conclusion, tape tenacity is identified as the most significant key process output variable during the above hypothesis testing. The next step under DMAIC is improve. Under improve, we'll cover conducting design of experiment, DOE, analysis of improvement. Conducting design of experiments. To improve the tape tenacity that has been identified as the reason for low fabric strength in the weaving department, the DOE at the extrusion line is decided to be conducted. Due to limited resources of industry and time constraint, only 4 factors with 2 levels and a half fraction factorial with 2 replicates are selected to perform the DOE at the extrusion line. Those factors are line speed, extrude temperature, water bath temperature, hot oil unit temperature. Results of DOE after conducting experiments. Fractorial factor design. Factors 4, run 16, replicates 2, fraction half. At the extrusion process, the interaction of line speed and the water bath temperature was found to be statistically significant. Figures 6a and b show that when the line speed is 300 meters per millimeter and water bath temperature is 400 Celsius, the tape tenacity has a higher value of 6.225 G denier, which shows a significant effect on tape tenacity. A strong negative correlation between line speed and water bath temperature value versus tape tenacity. To be cost effective, it is decided to use lower side temperatures for extruder and hot oil unit temperatures as they are not significant. For the attainment of maximum tape tenacity, the extrusion line process has been decided to run with the following new ratings as shown on table 15. For extrude temperature, a change from 255 to 250, and for a hot oil unit temperature from 90 to 85. In conclusion, for the attainment of maximum tape tenacity, the extrusion line process is adjusted. Analysis of improvement. Histogram of after tenacity before tenacity. Most of the values for after tape tenacity are exceeding the target value of 6G denier. Histogram of before fabric strain, after fabric strain. Data shows that due to improved tape tenacity, the fabric strength for the weaving process has increased. In conclusion, weaving sag rejection rate has been substantially reduced about 50% from 2.2 to 1.1. The last step under DMAIC is control. Under control, we will cover control plan and implementation process, determine improved process capability. Control plan and implementation process. To monitor the most significant process outcomes for Y's and input variables for X, a control plan is developed. Some of the activities included are total sag rejection, extrusion sag rejection, weaving sag rejection, cutting and snitching rejection, printing rejection, tape tenacity, weaving fabric strain. All these are monthly controls. Determining improved process capability. In conclusion, all values are in the control limits and the process is running efficiently after improvement. Conclusion. Conclusion key points. Sag rejection rate is reduced by 50%. An average sag rejection of 2.8% is found, which was reduced to 1.2% using DMAIC. The sag rejection occurred in the weaving department because of the low tape quality. The input of the weaving department was the extrusion process. The low tape quality was produced because of the lower values of the tape tenacity obtained from the extrusion process. In conclusion, process efficiency of a polypropylene bag manufacturing plant is enhanced by using Six Sigma. Thank you.